Good evening, everybody. On behalf of Ladies Study Group Kolkata, I welcome you all to our event with Dr. Shohini Ghose, who will talk on women in science, making invisible the visible. I invite Shohini onto the screen, please. Welcome to Ladies Study Group Kolkata, and thank you for giving your time.
Thank you for inviting me.
Shohini Ghosh wanted to be an explorer like Rakesh Sharma, the first Indian to go to space. She hasn't made it to space yet, but she did become an explorer of the quantum world. As a physics professor at Wilfrid Laurier University, Canada, she examines how quantum physics can transform computing and communication. Shohini aims to create a vibrant and inclusive scientific community as the director of the Laurier Centre for Women in Science. She is the recipient of several honors, including a TAID Senior Fellowship and selection to the College of the Royal Society of Canada's in 2019. She was among 25 young scientists worldwide featured in a UNESCO exhibit in Paris. She is the author of the book Clues to the Cosmos. Let's now hear what Shahrukh says.
Child, every Indian watching TED Talks India Naiba, what according to you is a job that cannot be done by a woman? Yeah, this is a trick question. The truth is, there are some natural tasks that we men are incapable of carrying out. But the same is not true of women. There is no task, no job, no profession that is beyond the reach of women. However, the sad reality is that women have traditionally not been encouraged to enter the STEM fields, which are science, technology, engineering, and math. But our next speaker will not let anything hold her back. Let's give an energetic welcome to well-known scientist, theoretical physicist, senior TED fellow, Shohini Ghose.
Proud of you, Shohini. Now the screen is yours.
Thank you so much, and thank you for this opportunity to speak with you. I'll try to live up to that introduction. Um, I'll tell you a little bit about the work that I do, but also I want to tell you a little bit about what it is to be a physicist and what a career and what the environment is like for women in science today. And I thought, given that we are living in these very interesting and challenging times, I want to show you an image that I think is a good place to start. Let me go ahead and share my screen. I hope you can see this. So this is the image that I want to show you. And if you happen to be in the pharmaceutical industry, this would be very familiar to you. This is actually one of these models that you see in chemistry labs, and it shows a very particular and important molecule. This is the molecule representing penicillin, which, as we know, is a very, very important medication, but also it is important in the history of the development of drugs, because understanding how it works and all of the chemistry was really, really a huge step in the future of drug development, healthcare, and also chemistry in general. And the reason we know this very special structure and we can build it in the lab in, using these little balls and sticks is because we can calculate how all these different atoms actually stick together and how they bind with each other. And that is actually based on the theory of quantum physics, which is my area. That's why I thought it would be a good starting point, because it's such an important area, because it's already impacted all of us. And now more than ever, we understand the importance of healthcare. The problem is, in fact, that this kind of calculation, where you understand and try to calculate the properties of molecules and atoms, is actually not that easy, even when you have the best supercomputers in the world. So, in order to do these kinds of calculations, you need special computing power. And even if you connected all of the computers in the world, the best supercomputers with the best facilities, you would still not be able to calculate all of the chemical properties of a molecule that maybe, let's say, has 300 atoms or more. So penicillin we can do, but if we really want to calculate things for more complicated kinds of examples and develop new drugs, we actually are limited in our computing power. Except part of why I want to tell you about the kinds of work that I do is because we now have a new way of doing computing, and that's what we call quantum computing. And that's the field that I work in. And it's offering us revolutionary possibilities, not just for drug development, but for many other kinds of areas, including environment and materials design and logistics and so on. So it's quite an exciting field to be in. And this is all based on being able to control these individual atoms and electrons, which we cannot even see. They are invisible to us. So I want to tell you a little bit about invisibility, because when I started off in this field, I always loved physics and I liked solving problems and the mysteries of the universe and so on. So I took a lot of physics classes, and then I found out that I know a lot about invisibility because my classrooms used to look a lot like this, where I was often the only woman, and sometimes the professor wouldn't even notice that I was in the classroom, and he'd say things like, good morning, gentlemen, things like this. So turns out that I was not the only one who felt kind of invisible. There aren't that many other women in the field of physics and generally in engineering and many other STEM fields. And if you look, actually, you can do your own experiment to see if that's true or not. If you go on Google, maybe not now, but later, you can do this for yourself. You can do a little search. So I did the search just to show you. Let's say you search for famous physicists on Google. What would you get? Well, Google, will do the search for you, and it'll show you a whole bunch of images of famous physicists. And here's what you will get. You'll get this nice banner showing you all the images, and you can see these are certainly names that you're probably familiar with. And you can keep scrolling. You see that there's a little button on the right. So I sort of went through and found all the different results that Google gave, and you get this. And if you scroll some more, you get even more of these images. And you may have noticed something. If you're very, very observant, you may have noticed one woman out of all of these different images. And I think you can continue, and you'll see even more of these images. But even Google knows that women in physics are invisible. So you might wonder, wait, what happened? I actually went and also dug a little bit more, and turns out that there are lots of studies done on this. For example, recently in 2019, there was a survey in Canada, where I live right now, because in Canada recently we had this really great, wonderful news that Donna Strickland, who is a Canadian physicist, won the Nobel Prize in 2018. So this was huge news, of course, all around the world, but also in Canada. So they did a survey in Canada asking people to name a woman physicist and expecting that at least people would name Donna Strickland. And the results were that they found that half of Canadians could not even name a woman in science. So this was kind of depressing, but it makes you wonder. Certainly it made me wonder as a scientist, what's going on? Why are there so few women in physics? And why is it that I kind of always feel invisible? So I went away as a scientist to do some more research. And again, there are lots of studies on what's going on in the field, what's the environment, what are the skills, for example, you need. There's this very common idea that physics and engineering, these require particular skills, and that's true. You need to do a lot of mathematics. You need to be able to calculate things. And then there's coming on top of that is this implication that somehow some people can do the math, others can't. In particular, I wanted to find out what's the difference in math skills between, for example, let's say boys and girls. Turns out lots of these tests have been done, and there's a standard assumption, somehow girls can't do math. But if you look at the data, here's an example. There's many studies. I don't want to show you everything. But here's data where students around class 7 or 8 students were given these standardized tests across many, many countries. All of the OECD countries actually participate in these kinds of studies. And students were tested on their science skills. And what's shown here is the results of these tests. And I know it's a little bit hard, there's a lot of data here, but really what's being shown is in some countries, girls perform better than boys. Those are the countries where you see the blue bars below the line. And in some countries, boys perform better than girls. And those have the bars above the line. India is not on this list because India doesn't participate in these tests, but there's other data I will show you. If you're interested in the country I'm in right now, Canada is slightly above the line, so boys do slightly better. But as you can notice, this is a little bit older data. There's also newer data from these kinds of tests. And in fact, in Canada, that's changed. So now girls do equally well as boys. And over time, these results keep changing. And the point here is that there's not a standard difference that boys always do better than girls. If there was really a difference in skill sets, then you would see it across the board in every country, no matter what. And you don't. Sometimes boys do better, sometimes girls do better. It has a lot to do with the environment, the classroom, the support structures, many, many factors. So that to me was actually encouraging because it means that if you get the environment right, everybody can do science. So I was quite happy. And in fact, this data, as I said, is also available in India. Here's some similar kinds of tests done to assess the skill sets in mathematics and in science in India nationally. And you will see here too, from the color coding, blue is where boys do much better and girls is where orange, the dark orange is where girls do much better. And the yellow is where kind of it's roughly even. And again, you see that sometimes boys do better, sometimes girls do better. It's not that it's universally blue across the country. Again, good news, nothing any different from anywhere else in the world. If you look at science particularly, you see a lot more blue, so boys are doing better in science, but not everywhere. There are places in India where girls outperform boys, which is great. But the point is that all of this is constantly changing, and it could be, and I hope at some stage in the future, you will see this map will be all just yellow, because that's where we really want to get to, so that everybody who wants to participate in the field can do at an equal level. So if there aren't any fundamental differences, what are the reasons why in physics particularly there's so few women participating? And unfortunately, that goes back to having to understand the culture and the environment and all of our own behavior patterns. So for example, this was an interesting study I want to show you, done in a science museum, where they observed how parents talk to their children in the science museum. And what they found, for example, was that parents spend much more time explaining the science to their sons compared to their daughters. And this was true for both mothers and fathers. And this is not because the parents were somehow doing it deliberately. They didn't even know that. This is only when you study this on a long-term basis do you find that there is this difference. They spend more time and they spend more effort. So there are all of these hidden ways in which we signal who is qualified and who we think should participate in science and who should not. And there are many, many such examples. I don't want to pick on parents and mentors, but they are a very, very important factor when young children are deciding what to do with their lives. Personally, I loved reading science books. I loved going to, or watching science shows like Star Trek. And I didn't feel too discouraged, which is probably why I ended up in physics. But there's all these other biases. For example, here's another really fun test where students around the world are just asked to draw a scientist. And this is the test that's been taken by thousands and thousands of students. And you might guess what they like to draw. I picked a particular example that I enjoy very much. Here it is. You see that it's clearly supposed to be this mad scientist, kind of like Einstein. Even E = mc squared is written there to show you that this is supposed to be about Einstein. And there's a bit of a, it's a good image as well as a bad image, which is why I like it so much, but it's a pretty fun image. And this is pretty standard. So almost nobody will draw a woman scientist. The majority of both boys and girls will draw a man in some, not all of them are going to look so funny, but it's definitely a clear trend even today that majority of such pictures feature a man. However, there's good news because sociologists have studied this a bit more. And what they did was this kind of an experiment where they had a woman scientist go into a class and talk about her science, not about being a woman or anything like this, just about her science. And she wore this multicolored jacket because she didn't want to have the white jacket stereotype or anything like this, like a lab coat. And after many weeks after she left, they did the same test again in this class. And they asked the students to draw a scientist. And what they drew, a lot of the students remembered and drew this. So this is showing us that you can actually change these kinds of perceptions. And it's very, very easy to manipulate us. So in fact, to me, all of this is good news because it means that where we are today is not where we need to be tomorrow. So someday, maybe when you do a Google search for famous physicists, Google will learn that there is a possibility to make women in physics also visible. There's another piece that I want to mention, which is that if women have the skill sets, and there must be other women who are curious like me and want to do physics, what has been their impact in physics already? Are they really no women, or is it just that Google doesn't know about them and should be told better, or the algorithm has to change to feature women? And the fact is, in fact, that there are certainly women who have contributed hugely. And in fact, the work conditions for these women have certainly been challenging. A recent survey shows that women certainly report having less resources. They do a majority of the child care, elder care, housework. They have less opportunities for promotion to leadership roles. And this is, by the way, universal, regardless of whether it's a developed country, developing country, country with more infrastructure, less infrastructure, it does not matter. Whether you go to Africa or Europe or anywhere in the world, this is the same universal trend you see across the board. So again, given that these are patterns, we know we can address them. So can we change resources? Of course. Can we change policies around childcare and elder care? Of course. Can we create opportunities for career advances? Absolutely. So all of this is changeable. And the one thing that really came out that I loved about this survey was that when asked, why did you choose this field, even though you know that this is not the case for me, and when you love something, you can change how we see this universe. And I want to tell you a few examples of women that perhaps you haven't heard about because they've been invisible, but they have done incredible things. For example, here's somebody, this woman named Vera Rubin. She was an American physicist and an astronomer. And what she did was she observed how galaxies, the stars in galaxies, rotate. And she found something that was literally invisible. She found evidence for dark matter by just looking at, oh, these stars, they're rotating too fast. She's the first person to notice it. And nobody quite believed that there's something called dark matter, meaning you can't see it. It is literally invisible. But she found a way to see the invisible. And in fact, now we know that dark matter, by the way, is far more common in the universe than regular matter that we see. So all of those stars in these kinds of beautiful images, that's the minority. Most of what we see is what Vera Rubin saw, meaning we can't really actually see it, but it's there. Somebody else who saw invisible things is this wonderful Indian physicist, Vibha Chaudhary. If you look at the left on this one image, you see these little dots and tracks, and maybe to you and me, it looks like little ants. But what these tracks are really the footprints of particles in the atmosphere that we cannot see, invisible particles. And by looking at these tracks and calculating energies and the momenta and how these tracks are shaped, Vibha Chaudhary and her collaborator Devendra Mohan Bose, who was in fact the nephew of Jagadish Chandra Bose, they found a whole new fundamental particle in the universe, which is something called the meson, pi meson. And this was the first step to building an entire theory of particle physics. So this kick-started the field, and they couldn't continue their study. This was done during the war in the 40s. They couldn't continue their studies because they didn't have enough resources during that wartime to get more equipment and gather more data. And so right after the war, some British physicist continued the work and found the exact same particle. This was a man named Cecil Powell. And in 1950, it was Cecil Powell who won the Nobel Prize for this discovery. And the year before that, another man named Yukawa won the Nobel Prize for the theory around this discovery. So 2 Nobel Prizes were awarded for the invisible particle that this woman found. That's the kind of impact that women have already had in this field. Speaking of other invisible discoveries, this is Cecilia Payne, and she was observing the sun. And if you look at the sun very carefully, well, you should never look directly at the sun, but if you have a telescope, maybe NASA, and you look at their images of the sun, it looks like this image on the left, because they can actually look at all the different parts of sunlight, all the different rainbow colors, and you see there's all these missing dark lines. Well, Cecilia Payne analyzed that pattern of dark lines using a brand new theory back in the day, which was in the early 1900s, and that theory happened to be quantum physics. She used quantum physics to actually figure out what are the chemical elements in the sun and in other stars. And she's the one who figured out that all of these different dark lines and the little hidden patterns of chemistry tell us that all stars are basically the same. They're made up of hydrogen and helium. And that is the entire chemistry of the universe. So this is the level of discovery that she made, and it's been called one of the greatest discoveries in astronomy. She did it as part of her PhD thesis. That's the first of the many, many other discoveries she made. And it has been called one of the greatest PhD theses ever written. So these are the women whose names should be up there with Einstein and Newton and the rest of those names you saw on Google, but they're not, but we can change that. And to me, again, this all means that there is real hope for me personally in my career as a physicist, because they give me energy and inspiration to continue. And especially Cecilia Payne, because she worked in quantum physics. So I too ended up in the area of quantum theory, and I too was focusing on invisible particles, which are these individual atoms. And eventually in my own research thesis, I didn't look for chemistry of the stars. I was looking at trying to see these tiny little atoms. Now, of course, we can't see them because they're too small. Speak of invisibility. But if you use a laser to shine light on these atoms, then the atoms actually interact with the laser and leave some kind of a shadow. And if you're very clever about it, then you can use the shadow to backtrack and figure out what's the image of these atoms. So to me, this was very exciting work, because it's very much like the kinds of things that Cecilia Payne and Viva Chaudhary, they were looking for invisible signatures of the universe too. So I worked with my colleagues on this kind of work for my own PhD. And one day we got an image from data of an actual atom. And it looks very peculiar because atoms they live in this very funny world where you don't know exactly where they are. So if you think of their world as kind of like this globe, you won't know where exactly they're located, because we can only know some kind of probability. Red is roughly where they're located and blue is where they're not. So this is sort of a representation of their location, a probability distribution. And we could take many, many such images of the atom. And if you lay them back to back, you can watch this atom as it evolves in its world and make a movie. So in fact, my colleagues and I were able to make this amazing movie and watch this beautiful atom that we cannot see with our own eyes. But here we are able to image something invisible and watch this atom move back and forth. And it's not just because we wanted to see something invisible, but it's because understanding the properties of these atoms will help us in this new field, which is what I was talking about, which is quantum computing. So from that time, which is when I first started, this was my PhD work. And then over the years, the field of quantum computing has evolved. And now we are at a point where we can control these individual atoms to be able to do tasks like calculate things. So here, for example, is a picture of an actual quantum computer that was built by IBM. Of course, we can't really build them in the lab easily. They take a lot of time and money and resources. So the white cylinder, there's two images here. The white cylinder is the quantum computer, which doesn't look like a computer, I know, because it's not like our regular laptops or desktops. It's a whole different type of computer. And if you open up that white cylinder, you will see this beautiful chandelier, which is this picture on the right. And even that is not actually the computer. All of the beautiful wires and such that you see, all of that is used to really control the processor, which is a tiny, almost invisible little chip right at the bottom of this chandelier. And everything else is just to control it and also to keep it cold. Because to make this quantum computer work perfectly, you need to keep it colder than outer space. Because if it heats up, it's like errors. You know how our laptops shut down when they overheat? It's exactly the same with the quantum computer, except for them overheating is actually not really the same as in our computers. So yes, the goal is to keep them colder than outer space, which is why you need a room full of control equipment to keep them working perfectly. But the quantum computer does work, and it can do some tasks, kind of like a toy prototype, to test and benchmark what we can do with these quantum computers in the future. One of the earliest applications of quantum computing and quantum information processing was actually in encryption. So you know how we have passwords, and even this kind of a conversation that we're having, the data has to be protected. Otherwise, hackers will do bad stuff. But even more importantly, we want to keep our financial data and our healthcare and everything else safe. So encryption is a huge, huge part of any kind of quantum information. Regular information processing. And quantum computers and quantum information gives us a way to do better encryption, completely unhackable encryption. How? Well, turns out that if you want to copy quantum information, you can't do it. It's just not possible to copy it. So this was one of the first quantum rules used to try to hide data. So this is kind of the reverse, where instead of trying to make something visible, we want to make our data invisible to the wrong people. So again, it always comes back to what it is we're trying to show and what it is we're trying to hide. So quantum encryption now is something that is slowly moving into commercialization already. For example, in India too, there is a huge effort to build a quantum encryption satellite-based network, which would be then used for all of our Wi-Fi communication and so on. And this is an ongoing effort. There are many, many different institutions in India that are involved in this. And there are countries all around the world actually working on this. In China, there's already an existing encryption network of this kind. But that's not the only thing. In fact, quantum can be used for, as I said, many, many applications. This kind of computing means we can do secure encryption and communication. We can build better drugs. We can build better systems for healthcare. We can make better searches and look at large amounts of data to understand climate change and the environment, or to sort through and keep our finances secure. Or even in today's day, especially, we know that things like supply chains and how food is distributed, for example, really important these days. So even that is an area where being able to optimize those kinds of processes is very important. And all of these are potential areas where quantum computers could have an impact. We're not there yet. As you saw, that giant room where this one computer was being operated is not at a scale where you can do this large scale computing yet, but we will get there soon. And when we get there, I hope we're ready to be able to responsibly use this technology. So not just governments funding this kind of work, but there's lots of startups and companies all around the world. The big ones like IBM and Google and Microsoft are certainly working on this, but there are also a lot of smaller companies. There are companies working in software, in hardware, as well as all of the side technologies in it. And this is a multi-billion-dollar industry happening. But I was wondering, who are the people who are working in this field other than researchers like me? So I went and looked up one of these new startups to see who are the researchers. And unfortunately, this is what I found. We're repeating the old mistakes, which is that we're still not at a point where we are moving away from women being invisible. So I don't want to leave you with this negative message. So instead of showing you this picture, of course, we have to work to change this. I want to show you another picture of how we are working to change this and build a community where anybody who wants to be part of this field can actually contribute. So recently, here's the picture. Recently, we held, I guess not that recently, but this is a conference that we held in 2014, but the more recent version was held in 2017. It's repeated in different areas of the world. This is a conference that brings together women physicists from all around the world. Everyone in this photo, all these women are physicists. So women are doing physicists all around the world. So it's not that we're not active in the field, it's just we're invisible. So part of what we wanted to do in this conference is to talk about this and understand where do we stand and how can we actually remove this cloak of invisibility and be fully recognized as part of this community and celebrate those who already have contributed to this community. So I guess I'll leave you with this wonderful, inspiring image, and I'm happy to answer questions. Thank you.
Presentation. And I'm sure after listening to your talk, many more girls will be inspired to take up quantum physics and be in the science stream and be more visible. Thank you. Now I invite our committee members, Mini Juneja and Enu Bala. They will take up questions from the audience. So they will be asking them. Mini, you please ask first.
Sure. Yeah. Good evening, everyone. Thank you for being with us today, Dr. Shohini. On behalf of the Lady Study Group, I would like to ask you some questions from the audience.
Sure.
We are all so fascinated by the evolution of the quantum theory and the role of the invisible women in physics. We'd like to know a little about your new book, which is slated to release next year, which talks about, of course, gender equality and about the lives of unheralded and under-rewarded women globally. So we want to know who has been your inspiration and why.
Wow. So some of the women who've been my inspiration, I talked about people like, actually, to be honest, when I was in school in India, I was never taught about Vibha Chaudhary. I don't know if you heard about her when you were in school, but she's certainly not in any textbooks. So only much later, I learned about her, and she was very inspiring. So I must say that when I was a little girl, as I usually talk about, I had role models. The women role models were not even real. They were imaginary characters, such as characters in Star Trek. So that's how hard it is to find women role models as a girl in STEM. So for me, the way it evolved was that, as I said, I was a curious person. I did have these sort of dreams of going to space, kind of like Rakesh Sharma, but I did see that in shows like Star Trek, there were women on these spaceships. I didn't really care that they were not real back then. So that's what got me started. And regarding the book, I felt that because these women are so invisible, I wanted to tell their story and show that, in fact, it's not just one or two here and there. It's not an exception. Throughout the history of physics, there have been contributions by women in almost every single one of these big theories, whether it's quantum physics or relativity or optics or cosmology. In every area, there has been some major impact by women. And so that's what the book is about, to tell that story.
I see. Thank you. So I have another question. The members want to know, how does the quantum secret sharing scheme allow 10 parties to communicate securely. 10 parties together. Yeah.
So broadly, okay, to really answer the question, though, would take a long time. There are entire courses about quantum cryptography, for example. But to give you broadly, the idea is that, in regular cryptography, when you want to communicate securely, or maybe you want to share a password, maybe the 10 people have a joint bank account and they just want to secretly share the password. Well, you take your whatever, let's say your password is whatever, 1357. Instead of sending 1357 on as a text on your phone, you have a secret key. Maybe you have to add the number 2 to each sort of number. So you send 3579 instead. So anybody else who is reading it will think that the password is 3579, but it's not. The person who has the key, meaning that the other person in your network, the 10 parties, they know that they have to subtract 2. So the number 2 is like a key. And the most important thing, of course, this is a very simple example, that key is too simple. Usually the key that you use is already hundreds of digits long. And so the most important thing for encryption is to keep the key safe. Anybody who has the key can use it and unlock. It's kind of exactly like a key to your home. You keep your key safe, right? Nobody else can unlock your home. Now, what quantum does in a network is provides a new way to keep the key secure. Meaning, it's almost like, let's say you've lost your bag with your actual key in it to your home, let's say, or you have the paper where you have the key password written. Somebody steals it and they have your key, right? The thing about quantum keys, even if somebody steals it or tries to read your key, the key itself disappears, meaning it's not readable. Yeah, isn't that amazing? It means that, the minute you try to read it, the key itself changes. It has no pre-existing value. So it's a completely different type of key. And the only way to go get around it and hack that key is you have to change the laws of physics, because the law of physics tells you that the key cannot be read. It's the rule of quantum that you cannot copy this information, and copying is the same as, in a sense, it's related to reading. So that's how quantum encryption works. I know it sounds like science fiction.
Really fascinating. Yes.
But
In fact, it's a dream for many of us to time travel into the future. Thank you for sharing this information.
It's like being in one of these science fiction movies in the future. Exactly. It's magic.
Thank you. I'd like Inu to ask a question, please. We can't hear you, Inu.
1 second.
Yes.
Yeah. Can you hear me now?
Yes.
Yes. So good evening, everybody. It has been such an inspirational talk, Dr. Shohini Ghose. So one of the participants who's watching the event has asked, who are the worst enemies of women physicists? The male counterparts? How many women physicists have won the Nobel Prize?
The worst enemy of women is the system. It's not it's not about individuals. We've created, we build these boxes, right? And we put ourselves in them, right? Here's the system, here's a box. In the physics box, you have, the men and the skill sets and so on and so forth. So it's not that men per se or an individual man is a problem. We are all part of systems where we are given roles and identities and, told which gates you can open and which gates you can't. So I feel like that's the problem. However, I guess I'm always an optimist, because boxes can be changed. You can remove those gates and unlock them and throw them open, and that's how we change things, really. Trying to, attack or point fingers at individuals will never help us. We really have to change collectively. The other question about women physicists, there have been, so the first ever woman to win a Nobel of any kind happened to be in physics, and that was Marie Curie. That was back in 1901. And then it took another 50 years for the next woman to win a Nobel Prize, and that was Maria Mayer. And since then, as I said, the third woman ever in history to win a Nobel Prize was my friend, Donna Strickland in Canada.
Right,
And then the
right.
fourth woman, and that's it, it's going to be a very short list. The fourth woman ever to win a Nobel Prize was it 2020? It was
Yes.
during the pandemic, and to me, it was one of these moments of hope during the pandemic. 2020 was Andrea Ghez, who was one of the group that was studying black holes. So, and that's it. Sadly, that's it. And if you look on, just the total number of Nobel Prizes given out in over all the years, I think it's something like 190 or something. So 4 versus, yeah.
So who has been your inspiration out of these women and why?
Well, they're all inspiring. They're all inspiring, as I said. My favorite, and this is why I always talk about her, is actually Cecilia Payne, because not just because of the fact that she literally discovered the most important aspect of the entire universe, right? Every single one of the trillions of stars in the universe. She found a universal description of them. But beyond her science, her life story is wonderfully inspirational, because of course she faced so many challenges. You can imagine in the early 1900s how hard it was to be the sole woman doing a PhD at Harvard. I'm not talking about just any old place. So she was able to do all this amazing work in that place, basically isolated in many ways. And she continued there after she got her PhD. They wouldn't even give her an actual faculty position or anything. She had no official designation. She was an assistant to the director, wasn't paid the same as her colleagues who were much less qualified than her for decades. Eventually, she was given the role of astronomer. She used to teach courses at Harvard, and they wouldn't list her courses in the syllabus as saying that she's teaching them. That's how invisible they kept her. And eventually things changed, and decades later, she became a professor at Harvard and the first woman to be chair of any department at Harvard. She became the chair of the astronomy department. And she did all this and developed, quantum physics. Was one of the first really amazing applications of quantum theory, which is my field. So putting it all together, she's incredible. So, yeah.
Thank you. Over to Imani.
Where is my?
And here.
There is an audience question. Can you hear me? Yes. As a scientist and also as an educator, what would you recommend in terms of how physics is integrated into the science curriculum for students in their high school years?
I think it's almost like you have to start earlier than high school, because by high school it's kind of almost too late, because people have already made up their minds. So I hear often people saying, "Oh, physics is so hard. I remember I just failed all the time in physics." Now, so to address that, you have to start a little bit earlier, and I think it has to become curiosity driven. The one thing I think that all kids have in common,
right?
We are curious. We want to pick up things and play with it. So we have to make it hands-on. Let people just play with different things, or start with a question like, why is the sky blue, for example? Or anything that, how can you, let's say if you like cricket, why is it that, spin works a particular way, for example? So engage people with, or especially kids, with their own interests and build physics into that, and that happens at a very early age. Because physics, honestly, is everywhere around us, right? When we walk, when we drive a car, when we turn on the light in our homes, everywhere you look, everywhere, physics is at work. So if we can sort of integrate it at that level, so that it's not something separate and scary, I think that's a way to really build. And it's not just for physics. I think it probably applies to other
everything, everything. Right, absolutely. There's one more question. Could you share some thoughts as to how quantum computing has or can be applied in the very real scenario of dealing with the COVID-19 pandemic?
That's a great question. And I had a previous chat that I did all about the quantum potential of pandemic. And I was thinking about this. As I said, currently quantum computers are in early prototype stage. So in this particular pandemic, quantum is not really, quantum computers are not going to be very applicable, because it's kind of like, back in the 60s, remember when we had the first regular computers like ENIAC and things like this? Well, nobody could have believed that we would have an iPhone back in the 60s, right? Yeah. And if you told somebody in the 60s, yeah, we'd all be chatting in this pandemic, let's say if we went to the 1918 pandemic, the flu pandemic, and told them, we don't, we'll all be staying, you'll all be staying at home and it won't be a problem because you can talk to each other through a screen. They'd think you were nuts, right? It would be unimaginable. So I think it's the same with this pandemic. We're not using quantum computers. Maybe, in a future pandemic, yes, quantum may be used in the back end, as I said, for the encryption piece, for things like integrating with healthcare records. You know how the contact tracing has been a big problem, keeping records and logistics of vaccinations, trying to avoid the fake stuff, the fake news, all of that. Anything to do with information processing where you need security as well as speed and privacy. Those are the kinds of areas that quantum could have a huge impact in the future, in such a way that the huge challenges of messaging and communication and fake vaccines and distribution, all of these could perhaps be done better. So this pandemic, we're learning all the things that we didn't do well. And those are actually exactly the things where quantum could help us, not to mention just developing the vaccines faster, developing drugs. We've got these new drugs being approved now, and it took 2 years. Wouldn't it be wonderful if it could take, 2 months instead? I hope. Maybe one day it'll be 2 days. You know how in Star Trek they just wave something and you have a new treatment. Imagine if you could do that. That would be fantastic.
Yes.
Well,
another question I have from the audience. They would like to know, how would the quantum internet differ from the current internet? Would it be faster? Would it be like, something new? They'd like to know.
It would be both. So I think that if you're talking about things like sending emails and doing WhatsApp, the average user will not see a difference, because you don't need to, you're not going to be sending emails faster than you can type, for example. Maybe maybe you can talk it to your
phone. There's a network issue.
You're not. Okay. Are we back?
Yes.
Yes.
Okay. So on the back end, on the security and making sure things are encrypted, nobody's hacking, that will all be hopefully, combined with our current internet, except you won't see those changes, perhaps. But
so is there a reason to worry? Is there a reason to worry? Do we, with this enormous power? Yeah,
absolutely. So I think that the question now, as I showed you, there are all these companies working. So I think there are 2 reasons to worry. One reason currently to worry is that we, as you know, our information is not that safe. And, yes. The current encryption protocols that we use actually would definitely be vulnerable to somebody. Let's say somebody builds a quantum computer. Then that computer would be used to hack everybody else, right? So there's this race. Everybody has to have a mutually assured quantum computing, destruction, I guess. But what if you flip that, to get to your question of should we worry? Yes. So who's going to be controlling that technology? Who's going to be building that first quantum computer? Is it going to be companies? Is it going to be governments? Is it going to be one big player and everybody else is, not going to have a say? We've learned that these things can go horribly wrong, very fast. Look what's happening with AI, there's blockchain, there's just regular computing itself, there's so many issues. So all of those kinds of technology rollout problems that we've seen in the past all of those apply to quantum, but even worse because the impact of quantum can be so big. So you're absolutely right that part of this process has to involve not just developing the tech, but understanding and regulating it.
Yes. Thank you.
Great question.
Okay. Now, where is Sucheta? Our Vice President will give the vote of thanks. Sucheta?
Yeah. Now, good evening, Dr. Shohini Ghose, Sumita Ray, Inubala, and Mini Juneja. Namaskar to all. Shohini, we much appreciate and are immensely grateful to you for talking to us and making the invisible visible. So, women in science, especially, sounded like a big inspiration for women. To me, you personally are like a genie in quantum wonderland for a happy future. Uncertainty was never known to be so powerful and sci-fi. Really looking forward to experiencing fluid quantum reality in healthcare, drug development, and encryption, to name a few. We are very proud of you and respect your dedication towards ongoing quantum research. Shohini, thank you very much. And I'm sure all the children in the world should watch Star Trek early in their lives. Thank you, viewers. Thank you, viewers and media, for all your support. Over to you, Sumita Di.
Well, we are all intrigued by the Big Bang, black hole, and the universe. Hope your research of quantum physics will one day unravel the mystery of universe. And I will not be surprised if your research one day will take the Nobel. Thank you so much, Shohini, for being with us.
Really appreciate the opportunity to talk to you all. Thank you.
Thank you.